Okay, now let's look at an example back to smart contracts where we're going to use hash functions in order to achieve some security guarantee in our smart contracts. So let's recall some of the general insights about challenges in smart contract design. Right, so even though we rely on the blockchain for availability and to run our program correctly, we don't inherently rely on it for secrecy or confidentiality. We also know to look out for issues like front running or things that involve time delays. So, with those in mind, let's go over an example of rock, paper, scissors. So, the idea of rock, paper, scissors is we're going to have a smart contract that provides three functions. The first function, two players are going to call to enroll themselves in the game. At this time, it's going to take a deposit of, let's say, one Ether token. In the second function, each player is going to call the input method and they're going to provide their choice. So they're going to choose rock, paper, or scissors. We're going to use integers 0, 1, or 2. Finally, after both players have made a choice, then anyone can call the check winner function, which is going to see who won the game and pay out the proceeds to the winner. Now, here's a code listing of an implementation in Solidity of that kind of design for a rock, paper, scissors game. Now, I'll pause here so you can look at this yourself and try to understand how it's running. In a moment, I'll give a walkthrough of it. But the thing to keep in mind as you look at how this works is that it suffers from several security problems that we're going to have to address in different ways, including with hash functions. Okay, let me give a quick walkthrough of this code listing. So this smart contract for a rock, paper, scissors game, it models each player as a struct that has two fields, so their choice, and then also the address of the player. That address will be used as the location where they receive the reward if they win. Right, the function add player, this is the only function that's marked payable because this is the only one that receives the deposit of Ether. Right, the require conditions here make sure that there aren't already more than two players and that the player actually put in the one Ether deposit necessary to play this game. Right, it adds the current value that the player sent to the reward field. Right, this is initialized as 0. And it creates a new player in the player method, in the player field, right, which is a mapping from integers to players. So player 0 is the first player 1 is the second player. And whether we're adding the first or the second player, it sets the corresponding mapping. It sets the adder field and the choice field to the corresponding values, and it increases the field representing how many players have signed up so far. Right, next, the input method, it simply takes their choice as a parameter. Now, the way it does authentication here, only players who have already registered can input, is that you have to provide the index of your player number, whether you're the 0 player or the 1 player. And what this function is going to do is check that the message.sender, so the address that immediately invoked this method, corresponds to the address that is stored in the corresponding player mapping. Right? And if this authentication checks, then it goes ahead and sets the choice value to the value that was passed in as an argument. Finally, the check winner method, right, this is going to return an integer of who won or not. And what this does is it looks up the choice field of the player 0 and the player 1, and then it has three if statements for each of the three cases of who won or if there's a draw. And depending on which of these three cases it is, it either sends the reward to the winner via the transfer method, or it splits the reward evenly among the two players. All right, now as I mentioned, there are several security problems in this implementation of a smart contract. So take a few moments and think for yourself about what are all of the design mistakes that you can catch, and what are the different kinds of security problems that show up in this smart contract. All right, let's go over a couple of the problems with this. So first of all, maybe the most obvious, given the setting of this, is the problem of front running. So the whole point of a rock, paper, scissors game is both players have to make their inputs at the same time. And the smart contract doesn't have any code in there that enforces that. So the problem is that the first player who makes their input reveals by publishing their transaction on the network what move they're making, rock or the number 0 in this case. Right? The other player can wait until they see the transaction figure out the input that was made, and then cast their own transaction knowing that they're going to be able to choose an answer that makes them win. All right, now as we mentioned, hash functions are going to be the idea here. So you can start imagining how you would modify the contract so that it avoids the front-running problem by using hashes. So we would modify the input function to have two phases, a commit phase and a reveal phase. In the commit phase, the players would just give the hash of their input rather than the input itself. All right, so we would collect a hash for H0, a hash for H1. Then after some deadline goes by, then we enter a reveal phase, and the two players would call a reveal function to actually give the input that they had already come up with. Now, this makes some progress, but if you don't see the problem, then you weren't paying much attention in the hash functions video, in the previous video. Right, if you watched that, then you should immediately recognize that the problem here is that these choices, rock, paper, or scissors, or the numbers 0, 1, or 2, those come from a very small input space. And that means that the hash of the particular value from that input space doesn't actually hide what it is. Right? If the player just commits to H0 as the hash of the string rock, or the number 0, then the opponent could just brute force try all of the three combinations that that value could be, and they know based on which of the hashes is the one that this first player input, he knows what their choice is committed to at that time. So he'd still be able to front run in that case. Now the solution is to make use of a larger space of inputs that we take the hash over. So the way that we can do this is by modifying the scheme so that instead of just committing to the numbers 0, 1, or 2, or just to the string rock, paper, or scissors, we include some additional random string called a nonce, or a number used once, that basically we add to the value before taking the hash of it. This means that the hash is more like a commitment. It binds us to a particular value that we chose, but it makes it a lot harder to determine what that value is, because now the inputs to the hash are drawn from this much larger space, which includes not just the particular choice from a small space, but also the nonce, which should also be large, like 32 bytes.